In this presentation, we want to look at linear speed and acceleration. This falls into one of the three primary categories of movement skills we'll teach within the context of this certification. So we have acceleration, absolute speed, as well as multidirectional speed. You'll find that many aspects of this acceleration presentation still have relevance to the absolute speed presentation. Therefore, there'll be some purposeful redundancy once you get into the absolute speed module. Let's start by taking a look at a couple primary objectives that we want to fulfill in this specific presentation. Number one, we want to define terms and compute basic physics problems related to sprinting. Now, this will be one example of information that has utility beyond acceleration. It's also going to highly apply to how we think about absolute speed. Therefore, you might want to reference back to this presentation prior to going into your absolute speed. From there, then, we want to identify and explain how specific kinematic and kinetic elements relate to the acceleration technical model. And again, kinetics and kinematics relative to the acceleration model will also highly relate to our absolute speed model. We then want to specifically recognize the coaching pyramid and identify the most effective cues for improving the acceleration technical model. All throughout this certification, we want to tie the what to the why and the how. Therefore, giving you the coaching insights that we use here at Exos to actually improve these movement skills is critically important. And finally, we want to identify and design effective movement skills programming for acceleration, actually providing you with the X's and O's of how you should design effective acceleration sessions, specifically to improve that initial burst, as we'll soon define from 0 to 20 yards. Now let's start by asking a question. What do we typically think about when we hear the word acceleration? Whether you were to ask your athletes or simply reflect on it yourself. Well, number one, at least when I hear acceleration, I think of a car. And within a car, what are we talking about? It's that 0 to 60 capacity. From 0 miles per hour, how quickly can I get going? And oftentimes we think about in sport, very similar. You could think of a scrum in rugby. Think of the positions that they're in. High angles, ability to move an opponent, therefore to allow the ball to get kicked on the outside and an individual to score a try. Imagine in sport when we talk about evasion, the ability to see a hole, get through a gap, or avoid some kind of opponent is critical. That burst, just like a car taking off, is central to the success of that individual. And then finally, we all know when we hear the word acceleration, when it comes to sport, we think of sprinting. How quickly can someone go from when that gun goes off to that 20-meter mark absolutely articulates how acceleration needs to come to fruition. So when we think about all these things, the central premise here is acceleration is all about getting going. Therefore, the science of acceleration gives us the insights on how you can coach and develop athletes that are good from that 0 to 60 mile per hour mindset. Let's start by framing up our technical model. Before we can actually get into the technical model of acceleration, we have to know the underpinning characteristics that allow someone to move in the first place. Therefore, a brief commentary around physics is critically important. Now, what we find is with testing data, you're able to do many of these physics calculations on your own. You can provide your athletes insights on their velocity, on their acceleration, even their force. Now, while many of these are average and not scientifically valid from a lab perspective, it can provide you great insights into getting a bit more understanding of the technical process of acceleration in this case, but also absolute speed. Let's define a couple key terms, and this might be a reminder for some of you that took physics and biomechanics back in the day, but these terms are critical to understanding the overall underpinnings of movement skills. Number one, kinetics. It's the study of forces acting on or produced by an object. Therefore, we want to understand the magnitude of force that a person presents into the ground has an equal and opposite action on their body. Therefore, kinetics is critical to the person actually moving. Force is the material by which power is built on. From there, then, we want to think about kinematics. It's the properties of motion in an object without reference to the forces causing that motion. Therefore, kinematics very much so speaks to the qualitative nature of movement skills. And does the motion map to how the force actually needs to be generated, in this case, in the ground? The second set of definitions that we want to bring our vision to is scalar versus vector quantities. And very much so conceptually, both of these definitions are critical to how you go about coaching and developing linear speed. From a scalar perspective, it's a quantity that has a magnitude but no direction. So things like simply speed and distance. Whereas vector quantities are a quantity that has a magnitude and a direction. So when we think about sprinting or change of direction, it always is about two things. How much force can I put into the ground? What direction am I putting that force into the ground to move my body in a desired direction, and how fast can I do that relative to sport and life demands? Therefore, typically when we're talking about movement skills, we're talking about vector quantities, factoring in both the kinetics, the force, and the kinematics, the motion that caused that force in terms of our description and our coaching. Now, no good discussion around speed, let alone physics, would be done without Newton's first law of inertia. Let's break this down and discuss how it actually imparts some influence on how we coach linear speed, specifically acceleration. We know this: an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Therefore, if someone is running very slow and needs to burst and accelerate, or someone's going at 0 miles per hour, such as the case in a sprint, specifically a 100-meter sprint, and needs to get going suddenly, they need to break inertia. There are unique characteristics of both force and motion that allow us to overcome inertia, thereby increasing our speed, i.e. acceleration, inevitably allowing us to rise into this absolute speed position that we typically call max velocity. Therefore, all the coaching that we do oftentimes when it comes to acceleration is to break inertia, simply because I have the majority of my inertia telling me to stay still into the ground, and I need to take that and move that inertia, inevitably momentum, in a forward position. So let's start then by defining one of these first key terms within kinetics and kinematics. And we're going to first look at a vector quantity that we call velocity. And we all know when it comes to speed, velocity is the name of the game. But let's look at how we can actually calculate it so you can do this at home with your testing. So velocity at the end of the day is distance in meters divided by time in seconds. Let's use an example of Mr. Usain Bolt in the 2008 Olympics. He covered the first 10 meters in roughly 1.85 seconds. If we remove his reaction time, we can see that 10 meters divided by the actual time it took him to run it, 1.685 seconds, results in a velocity of about 5.93 meters per second. Understand, though, that that velocity is average. It's not instantaneous. As we'll soon see, he's going to go a lot faster than 5.93 meters per second by at least his third step. But his average velocity over that 10-meter time period is 5.93 meters per second. Even average velocities are important if we look at distances like 100 meter. So if we take that and then extrapolate it, here's exactly what he did in those 2008 Olympics. We can see, number one, two defining features. We see an absolute zone of increase in speed, and then we see much more of a zone of maintenance of speed. Look at the actual graphic. Over 0 to 20 meters, all the way up to 30 meters, we see a robust increase in the overall average velocity. It's only between 70 and roughly 90 meters that we truly see that velocity start to stagnate or flatline. And only at the end, likely because of his celebration, from 90 to 100 meters does Usain Bolt actually slow down. One of the greatest things about him is his ability to hold his speed longer than most athletes, primarily because of his height and his ability to get at such high speeds and hold it because of his limb lengths. So when we start talking about acceleration, this further defines why velocity from 0 to 20 meters is such a strong defining feature of how fast someone can accelerate, burst through that hole, or get out of the blocks. Now we think of velocity, here's something interesting. Let's actually look at instantaneous velocities over the first 3 steps. And why are we looking at this? Because oftentimes in sport, it's those first 1 to 3 steps that dictate whether they make the play, whether they got through the actual gap, whether they got in the end zone. Therefore, from a coaching perspective, many of our techniques in terms of how to optimize acceleration really live and die by the capacity to get going and express that in at least those first 2 to 3 steps. If I can extend my acceleration longer than that, awesome, I have open field, but it's that burst that's the stopgap within effective acceleration. So let's take a look at our graph here. We are talking about block starts. So imagine someone's coming out of a 2-point start or a 3-point start. This can be analogous to that. We basically have 3 time periods. We have the time between starting to push into the blocks until their first foot hits the ground. And then we have the time from the first foot hitting the ground to the second foot hitting the ground, and that's what we call step 1. And then the second foot hitting the ground to the third contact, which is what we call step 2. If we look at block clearance, this means this is the velocity that the person is at simply when their feet leave the ground or leave the blocks. They're already going roughly 4 meters per second. But specifically now, go to contact 3, which is at the end of step 2. What do we see there? The person's going at 7 meters per second. Well, here's what's interesting about that. Elite sprinters can only run at around 12.2 meters per second. So by the end of the third contact, the end of the second step, they've already achieved over 50% of their maximal velocity. Let that resonate, because it is in those first 3 steps that oftentimes sport lives and dies. Therefore, everything that we're going to share today is about optimizing not only those first 3 steps, but everything beyond. But it is within those first 3 steps that we see the linchpin for successful acceleration capacities. Now that we understand velocity, let's take a look at acceleration, the actual quality that we're trying to improve with our acceleration technique. So by definition, acceleration is the change in velocity, again read as meters per second, divided by the change in time. Therefore, the overall reading from a metric per second is meters per second, right? And this is the acceleration that we're trying to actually maximize with the acceleration technique that we're teaching. So again, let's look to Mr. Bolt in 2008 at the Olympics. So again, he covered that 10 meters with his reaction time in 1.85 seconds. We subtract that reaction time, once again, 1.685 seconds to go just 10 meters. We factor in the change in his average velocity. So he started at 0, and as we saw in the previous slides, he ended up on average going 5.93 meters per second. These are all averages, giving him a net average horizontal acceleration of 3.52 meters per second squared. Now, that might not mean a whole lot until you look at the graphic of his acceleration over the course of 100 meters. This parallels what you saw in that velocity graphic, in that we see a rapid rise in acceleration all the way to 20 meters. But what do you notice after 20 meters? That acceleration progressively goes down. It's not that he's slowing down, but he's not speeding up as much. Therefore, his acceleration is a little bit lower. This continues to hallmark why, as we will soon see, that really 0 to 20 meters or 0 to 20 yards is what we identify as the true acceleration zone, primarily because of the physics definition of acceleration as we're defining here, and therefore the technique that leads to those optimized characteristics. Now, once we understand velocity and acceleration, again, both vector quantities that have a magnitude and a direction, let's now start to highlight a bit more on the magnitude and bring in Newton's second law for force. The acceleration of an object, as produced by a net force, is directly proportional to the magnitude of the net force. Therefore, everything has an equal and opposite force. So if I put 1,000 newtons of force into the ground, I'm going to get 1,000 newtons back, specifically in the direction by which I applied those forces. Therefore, we need the kinematics, the quality of the motion, to direct the magnitude of the actual forces, the kinetics, by this law, in the same direction as the net force and inversely proportional to the mass of the object. Therefore, this brings in the concept of how important body weight is to not only breaking inertia, but optimizing the acceleration of an object. I like to joke, but in all seriousness, the nutritionist is one of our best speed coaches. Because if we can help an individual drop their body fat composition, make their body a bit more of a robust athlete, take off any unneeded mass, that immediately allows them to have the opportunity to run fast. So if we optimize body weight, optimize the magnitude of force by getting athletes strong in the weight room, and then help them with proper coaching, learn how to direct that magnitude correctly into the ground, that is how we optimize not only acceleration, but also absolute speed and multidirectional speed. But let's take a little bit more of a look now at force itself. So what's the equation for force? Well, again, it's mass. That's what we have to factor in body weight. So mass in kilos by acceleration, again, meters per second squared. If we look at this equation, let's take an athlete, an average athlete that we might see, which is 82 kilos, which correlates to about 180 pounds. That individual achieves 6 meters per second and roughly 0.65 seconds. So now we have load, body weight, but we also have change in actual speed. So we take that load by the change in speed, said differently, which is acceleration, and that gives us our average horizontal force of 757 newtons, which fundamentally relates to about 170 pounds of net horizontal force. Therefore, for a person to go 6 meters per second in 0.65 seconds, if they weigh 82 kilos, they need to produce roughly 757 newtons of horizontal force into the ground, correlating to about 170 pounds. Now let's take a look at the actual force characteristics we observe over the first couple steps, similar to how we looked at it for velocity. Because again, the instantaneous amount of force needed to get the body going is very much so different than the average story that we are seeing here. So this is an example of the actual block start that an athlete would go through. So you can think of this paralleling a 3-point start, or even to a degree, a 2-point start. Our blue line represents the total force of both the front leg and the back leg. The yellow line specifically references the back leg, and the red line specifically represents the front leg. So a couple things that you notice. That back leg plays a critical role, especially in block starts. Arguably at a 3-point start or a 2-point start, because you don't have that block behind you, you can't get as much dig, but still that ability to get that inertia moving forward and getting forward momentum because of that back leg, oftentimes called the quick leg, critically important. We then see that combines with the front leg to give us that peak force of roughly 1,200 newtons coming out of the gates, which in most cases is going to be about 1.2 times an individual's body weight based on how much they weigh going in. From there, then, what do we notice? Well, that front leg obviously continues to push, giving another spike in force. Well, why do we see that second spike in force? Well, the reality is, when I'm in that deep 3-point stance, I'm at a mechanical disadvantage. It is only as I approach toe off that I get in a mechanically advantageous position, allowing me to once again increase force from that baseline. Both of those legs contribute together to allow me to optimize that acceleration off the blocks or out of my stance. Again, if I can overcome my body weight, achieving that some half of my max velocity by that second step out of my actual start position. So force is the material by which velocity utilizes to actually get going. Force times velocity, again, is power. Force is the material power is built on.